Okay, so we're going to look at situations where a geometric series has a limiting sum. So we'll start with this problem with the rabbit. So the rabbit starts at the center of a circular garden which has a radius of 20. He is jumping halfway towards the edge of the garden, and as you can read, he jumps half as far with each jump. So on his first jump, you guessed it, he's only jumping 10 centimeters. Second jump is half as far, so 5. Third jump is half as far, so 2.5. And the fourth jump, half as much, so 1.25. So if you've got your arithmetic geometric sequence radar on, you'll note that this is a geometric sequence. And when we talk about the total distance that the rabbit has jumped, on the first jump he's only jumped 10 centimeters. It's quite a small garden. The second jump, 10 plus 5. So 15 centimeters. On the third jump, 15 plus 2.5 centimeters more, so 17.5. And then one more time, 17.5 plus 1.25 is 18.75. So hopefully you're observing that. You certainly know that as you are adding the first and the second and third and fourth, and so on and so forth, that we're adding on smaller and smaller numbers. It's definitely approaching something, and just at a guess, it looks like perhaps that sum is approaching, it being the sum 20. So in the next example, certainly this is showing you that the sum of this particular geometric sequence definitely has a limit. In the next example on page 37, we'll consider the formula for the geometric series. So let's keep going to page 37. Here we go. So we're just going to so-called take cases. So consider what's happening to this formula. So consider the sum when r is greater than 1. So pick an easy geometric sequence. So 2 that we're going to add, so geometric series 2, 4, 8, 16, and so on and so forth. We can see that, obviously see that the sum increases without any limit. It's going to go to infinity. So, well, let's consider another case. Let's consider the sum when r equals 1. So, for instance, picking an easy example, 5 plus 5 plus 5 plus 5, and so on and so forth. Again, the sum increases without limit. So, if you're thinking, you probably already know what's going to happen when we consider when our common ratio is less than 1. So let's again pick something easy. 2 plus 1, half it, plus half of that, plus another half of that, plus, and you know that we're adding smaller and smaller and smaller values on. So therefore, we know that this is approaching a limit. And so let's consider the formula above. So say, for instance, I'm working with, we know in this case, A is 2, our common ratio. We're halving everything, so we're multiplying by 1/2. So let's say we build this formula where we've got 2. I'm going to use the formula 1 minus r. So power of n on 1 minus 1/2. So consider this. What's the limit of this sum as n goes to infinity? So I'm asking, what's the limit as n goes to infinity of 2, 1 minus 1 on 2, oops, to the power of n. You need to squeeze that in there, and then a bracket, and 1 minus 1 on 2. So we know this value, that's approaching 0. So really what we're calculating here is actually 2 on 1 minus 1 on 2. So if we do that arithmetic, that sum is approaching 4. So find the value of the limiting sum if we generalize this. So B is saying find the value of the limiting sum. So limiting sum implies that we're finding the limit as n approaches infinity of, let's generalize that formula, a 1 minus r to the n, 1 minus r, assuming r, absolute value of r is less than 1, we actually have this formula that's a 1 minus r, because again, that's going to 0. So that's just a times 1 on the top. So therefore, this will work if and only if. Let's put it in this format first. If your common ratio is between -1 and 1, or that absolute value of your common ratio is less than 1. And therefore, if that's the case, we have a limiting sum, and it's going to be a on 1 minus r. And again, this formula for the limiting sum is on our reference sheet on the first page, upper right-hand side. Okay, so I'll leave example 316 for you to do, but I just want to highlight a phrase here so you don't go down a deep dark rabbit hole and get yourself spinning, provided that they exist. So the only way that we won't have a limiting sum, remember that requirement that the absolute value of your common ratio has to be less than 1. So you might want to check that first before you start digging around and working with finding the limiting sum for A, B, and C. All right, so what we're going to look at is, if you can progress to page 39, we'll work with this 2 meter tall tree. Sorry, looks like my iPad is having a bit of an issue with showing that upper left hand corner. So take a moment to read that we start with a 2 meter tall tree. Oh, there it goes, thankfully. And each of the first 3 years, the tree grows by 1 meter, then 2/3 meters, and then 4/9 meters respectively. So just outlining this growth, so just the growth, the first year it's going to grow 1 meter. In the second year, it's going to grow 2/3 of a meter. In the third year, it's going to grow 4/9 of a meter. So therefore, if it continues to grow in this pattern, first of all, is it an arithmetic progression? There's nothing here that implies that it is, so I would definitely check that and see if T2 divided by T1 So 2 on 3 divided by 1, that's a common ratio of 2 on 3. 2 on 3 divided by 2, sorry, the third term divided by the second term is 4 on 9 divided by 2 on 3. So same, change, flip. And multiplying and reducing, yep, there we go. We definitely have a geometric progression there. So our starting term is 1. Our common ratio is 2 on 3. All right, so how tall will this tree be after 10 years? So notice 2 isn't actually part of our progression. It's just how tall the tree was before we started noting this geometric progression. So in so 10 years, we know that the total growth, we're talking about a sum, is 1 minus 2/3. Talk about 10 years here. And 1 minus 2/3 in the denominator. So calculating that, that's 2.95 meters. So it's going to grow 2.95 meters in addition to what it started to. So therefore, how tall will this tree be after 10 years? The tree will be, started at 2 and it grew an additional 2.95 meters. So it's going to be 4.95 meters tall. Now, noting that our common ratio is less than 1, it does have a limiting sum. So therefore, it's asking find the maximum height to which this tree will approach. So it's actually asking for the max height is actually really the limiting sum. So sum equals a 1 minus r. So that is, ooh, and not forgetting the fact that that's on top of, that's how much it will grow in addition to the starting 2. So we're talking about 1 on 1 minus 2/3. So that equals 3 meters if we do that arithmetic. So max height is, it'll grow an additional 3 meters on top of its starting height of 2. So its max height is going to be 5 meters. I will leave the rest of them for you to do, noting that. Have a go on 18. It's a wee bit of a tricky one, but it's definitely what I would consider an unfamiliar problem. I'll leave that to challenge yourself. And I would encourage you not to look at the solutions until after you do try to have a go at 318 and see if you can formulate a response. Good luck with that one.